Okay, so welcome to the fifth and final part of lectures on physical metallurgy of zirconium alloys. In this final lecture, I'll talk about thermal creep, rate theory, radiation growth, and irradiation creep. Now, thermal creep in the context of what we're interested in with respect to nuclear materials really applies to fuel storage. That's where thermal creep is a concern. I don't have too much to say, but I do have a comment on some of the work that's been published, primarily by French. The French had a substantial program looking at thermal creep. And here's some data that was produced by Soniak et al. Some years ago, about 15 years ago, 2002, 18 years ago. 22 years ago, sorry. Here we go. One thing you'll notice is that they have creep here for different doses of exposure of cladding. Now, I think that the cladding, the fuel cladding, was exposed at whatever the operating temperature was, but somewhere between 320 and 350 degrees C, I guess. And so they're testing it at 350 degrees centigrade and a high stress. Now, one of the things that you'll notice is that in the unirradiated case, it's a very high creep rate. But when you look at the doses here, they're very high doses. These doses are an order of magnitude larger, more than an order of magnitude larger than the type of doses I've been talking about earlier, where we get saturation in the A-type damage. So a lot of this hardening we see here, reduction in the thermal creep rate, out-reactor thermal creep rate, has to be because of some other feature. Either that or the doses are wrong. I just don't understand it. But one thing that comes to mind that would be a feature that does evolve over a long time is the C component loops. And fortunately, the French did publish some work, Bordelot et al., where they actually showed some images of material after creep testing. And to me, I recognize it straight away. There's some C component loops in this material. And this relates to the same program as this. So one of the things I take from this is that the suppression here in the thermal creep rate after irradiation that continues up to very high doses is because of C component loop formation. So how do we relate all the microstructure variables to the actual behavior in reactor? So now I'm going to shift to in-reactor deformation, not post-reactor, post-radiation creep testing. And I want to talk about rate theory, which is a very simple way of assessing how a material behaves. Now, two of the more important parameters to use in rate theory are the vacancy migration energy. So you have to understand something about point defects to know what we're talking about. But basically, it's you have a jump frequency or a migration energy which applies to point defects, and on the left-hand side we have the vacancies. And the peculiarity with zirconium, unfortunately, is that it's anomalous, not what's called anomalous diffusion. So what results show is that at higher temperatures, as we get to high temperatures, the migration energy, which is the slope of this curve, decreases compared to low temperatures. Now, this is attributed to iron coming into solution because it's a method of, you may have heard of it before, like facile vacancy motion in the presence of iron. And although this is at high temperatures thermally, when the iron gets dispersed into the matrix, during irradiation, one of the characteristics of radiation is iron gets dispersed everywhere. And I mentioned this before. And many of the reports, people doing theoretical studies, attribute the migration energy of vacancies during irradiation, even of what's at 300 degrees C at lower temperatures than this down here, to this kind of low energy migration energy, say between 0.6 and 1 eV, not the high energies here. So typically for modeling of irradiation effects, we tend to assume that we have a low vacancy migration energy because it's what fits, what gives us reasonable agreement with data. The interstitial issue, interstitials have very low migration energies compared to vacancies, but one of the more important things about interstitials in zirconium is that the diffusion is anisotropic. So what that means is that within the basal plane, the diffusion of the within the basal plane, the diffusion of the interstitials is faster. You have a lower migration energy within the basal plane compared to inclined to the basal plane along the c-axis. So how do we put this together? Here's just an illustration of the way one would put together a rate theory, and really it's just about balancing point defect flows. So these are the equations you would use. There's the diffusion coefficient, and the issue is about determining what the steady state concentration of interstitials and vacancies are during irradiation and how quickly they go to various sinks. So I don't want to get into the details here, but the essence of rate theory is to simply, we displace a bunch of atoms, we have holes left, and then it's a question of determining what rate these atoms and the holes migrate to various sinks. Well, the rate which they migrate to sinks is actually dependent on their production rate, because the rate at which they diffuse is so much faster than the production rate. The rate determining step is actually the displacement damage rate. So we have a situation like this. One can build up a model and you can include dislocations or dislocation loops or cavities or whatever you want that is appropriate for the microstructure, and also induce some directionality, especially that's important when you have interstitial diffusion, which is anisotropic. And one builds up a model when you construct a microstructural framework. Here's a simple framework where I'm looking at the fluxes per unit atom displacement, and this is G is the damage rate, dependent on the density of the A-type dislocations and C-type dislocations. And what you find is that there's a maximum in the rate of strain. Now it's the rate of strain which is in the absence of stress, in fact, because there's a bias. You get more interstitials migrating to A-type dislocations. Tons of work over a 50-year period about biases and interactions with dislocations and point defects. You just have to accept for now, if I tell you there is a bias, one can assign a bias to different types of defects, and that's just gives you an idea of how readily that defect is going to absorb one different point of defect. And then if we apply a stress, we change the bias. One of the interesting things about the rate theory calculations is you can calculate the point defect, steady state point defect concentration as a function of temperature and damage rate and dose, and with dose you're increasing the point defect sinks in the form of dislocation loops. And what this shows when you do it for a typical zirconium alloy is that around about 360, 380 degrees C, one expects that certainly the vacancy concentration does not exceed the what would be thermal. This dotted line is the thermal is basically thermal diffusion. It is what you would get thermally for a rate of flow of vacancies. So, and at these high temperatures, 420, 440, it's higher than the interstitial. So here, thermal effects dominate. So we talk about radiation growth. I mentioned about the growth is dependent on the ratio of the C and the A dislocations. So we have data on this, the A-type and C-type structure. As I said, A-type, at the beginning of irradiation, the A-type loops evolve and reach a steady state condition. So what we're interested over very large fluences is what's going on with the C component defects. So the recrystallized material shows an incubation period before the C loops start to evolve, and the cowork material, it starts evolving right from the get-go, from time zero. To illustrate that with some TEM, here's some data on irradiation growth, and it just shows that when you get to the high growth rate, it coincides with the formation of C component loops, which we can model very easily and very simply. In the co-work case, we have all these screw dislocations that are present to begin with, and when we irradiate, we get a lot of helical climb on these existing screw dislocations, and a much more accelerated evolution. Fundamental studies in fast reactors like EBR2 show that we always see this effect, that when the growth rate is high, we see a lot of C component defects, but we also see a lot of variability depending on what alloy we're talking about and whether we have different levels of impurities. So one of the things from that EBR2 study that became apparent is that if you have pure zirconium, you don't, for a given dose of irradiation, we don't get any C component loops, but if you have impure material, you do get a lot of C component loops. And then when we look at where the C component loops are, they tend to align up with kind of layering, segregation of impurities. So they go on hand in hand. Now, at low temperatures, we tend not to get loops formed for whatever reason, either because the impurities are not there or because things are so sluggish. But if you have a dislocation, like a C component dislocation, you will get helical climb on that dislocation. And this is an example from zircaloy, irradiated at about 60 degrees centigrade. So we don't get any C loops at low temperatures, but helical climb. And the helical climb occurs by point defect absorption on the dislocations. Here's an example showing this helical climb in this case it's at 300 degrees C, though I haven't said that, but it is, I can tell you that. This is at 300 degrees C, and we get this helical climb, low dose, increasing dose, 0 minutes, 3 minutes, 30 minutes in a high voltage microscope at 10 to minus 3 dPa per second. Sorry about that, I should have put the temperature. Here's a case where I did some analysis and analyzed this loop, and then I re-irradiated it in the reactor so that when we look at it subject to some damage in an electron microscope, you can see the loop evolving. I already know that this is a vacancy loop because of the analysis that I've done. So I know that is preferentially absorbing vacancy loops. And this is a very important aspect of modeling. Many years ago when I was a student, I did some analysis on some faulted loops, and I'm putting this in because I have to correct something that was published. In that case, I identified some loops, and I thought that they could be identified as half or bar 1. Very recently, I was doing a lecture and I was teaching people how to do defect analysis, and then I realized that I didn't have enough information to show that the loops were actually that. I was missing one piece of information, which was information I would get from this region. But because my full normal was here, I could only get to a certain part of the Kikuchi space, so in order to do the analysis. So what that meant is that what I'd have to say is that the loops are either half O bar 1 or 6-2 O bar 2 bar 3. The important thing is not the Burgers effect. The important thing is that they're vacancy. So vacancy loops grow with electron irradiation, whether you got them there prior to from neutron irradiation or whether you create them during electron irradiation. So irradiation creep, I've got 5 more minutes to talk about radiation creep. Peter in his talks later will be talking about creep in BWRs and PWRs. So I'll just introduce Candy Reactor. Candy Reactor is typical 600 megawatts of 380 channels. And the problem with creep there is that these channels are horizontal in the reactor, and if they sag, which they do over time, they interfere with reactivity mechanisms. Likewise, the feeders for the coolant, inlet and outlet, start to interfere with each other when these channels elongate. The fueling machine can't engage, and also if you get to at certain points in the channel, because of the temperature and flux, the creep rate, the diametral creep rate, can increase to the point that you get a lot of the coolant flowing above the fuel bundle, and therefore it gets hotter down the bottom, which naturally is a safety concern. So what is creep? Irradiation creep? Well, here's some examples to show what happens when you irradiate. If we have a low flux, in the solid lines we see here, we have axial and diametral creep of a creep capsule, and then with a higher flux, as shown here, these fluxes here, we get higher steady state creep, although the primary creep is about the same. And the primary creep really amounts to the time during which the microstructure is evolving to harden the material. Well, actually, it's not. It's occurring over a much longer period, but there is some other effect here, which is hardening the material. So over a large dose range, what do we see in terms of creep? If we express the creep in terms of the strain per unit or per neutron in effect, what you see is a very high creep rate early on in the irradiation, and it very quickly drops down to some steady state value with time. This transition here to this low rate corresponds with this increase in the A-type loop structure, and what's happening here in the longer period will be affected by the C component evolution, somewhat similar to what I was showing you with the French fuel cladding. This is some data now from creep capsules showing exactly the same thing, and here we're comparing different tubes, creep capsules here, and what you'll notice is that the creep rate is actually continually decreasing, and that's consistent with the C component loop structure evolving. So that can be explained based on this kind of evolution in the microstructure. So ultimately what it boils down to is irradiation creep is a combination of dislocation slip or diffusional mass transport. The diffusional mass transport we can model quite easily, and so the slip, but we have to model them in a different way. In the one case, we attribute the strain step to the movement of the dislocations, to the glide of the dislocations, and in the other case, we're just simply talking about diffusional creep. So bearing that in mind, if one knows, if one has something like a pressure tube, a fuel channel like this, where there's a range of fluxes and temperatures, and we can measure some of the microstructure. Oh crap, okay, that's gone ahead. And we can measure the microstructure with X-ray diffraction. When one inputs the microstructure from the radiation damage, combines that with the microstructure from the dislocations, the microstructure from the grain boundary sinks. If one combines, throws everything into the pot, so to speak, creates your damage, and then decides where everything is diffusing, which was simply balancing the mass transport, one can then model the creep of the of the pressure tube. In this case, it's a predicted diametral strain rate, and I've got the prediction, which is my lines here, and this is the data for three particular tubes in the Bruce 8 reactor compared with standard tubes. So these particular tubes were experimental tubes, which were unusual, but all I've done here is put in the microstructure for these tubes compared to the microstructure for these tubes. So the modeling gives us somewhat close to what the reality is.